in a very short period of time. Oh, well, I guess I put up this slide here before we start talking about muons just to remind us of, it seems like we have done a lot this chapter. There were, we have the basic time dilation result that says when you watch a clock moving by you at high speed, you're going to see it run slowly compared to normal. And you have to be careful of what it means when we say see, because you can't trust just one person to look at it and just regard the photons coming into their eyes. We're going to want local people to make measurements. There were several other objections that are grayed out here. I'm not going to comment on them. But probably the most important comment is what we spent most of yesterday on, which was this, what most people will point out right away. It sounds paradoxical to say, I see your clock running slowly, you see my clock running slowly. Isn't there some problem with that? And there's an additional complication which says that, well, everybody, of course, when they're in an inertial reference frame, wants their clocks to be synchronized. And we're always going to assume that within an inertial reference frame, everybody keeps their clocks synchronized because that just makes everything simpler. You don't have to account for one person having their clock reading noon when another person in their inertial reference frame has their clock read 1 o'clock or something like that. So we'll assume everybody's within an IRF, clocks are synchronized. Unfortunately, we're going to find out in chapter 7, and I'm just giving you a little bit of preview, and Merman doesn't give you that preview, which makes it sound really mysterious, like he's hiding something for later. In other reference frames, those clocks that are synchronized in my IRF as viewed from another IRF are going to be seen to be not synchronized. And so that effect makes us, it means that we have to be careful when calculating the time interval between two events, because if two clocks aren't synchronized, from my point of view, then if I try to infer what that person in the other frame who's got the non-synchronized clock is going to measure for the time it takes me to get from event 1 to event 2, if I'm traveling between those two events, is going to be not quite the whole story if I just take the time dilation into account. Because I would say, oh, their clocks are running slowly. Whatever my wristwatch is that I read for the time it takes me to get from Earth to Procyon or wherever I'm going, whatever my watch is, their clocks are running slowly, so theirs should read less time, when in fact they read more time. And that's because of the asynchronization of the clocks. One clock started out ahead of the other clock. The place I was heading toward started out ahead, so they actually record much more time than I might naively infer. Okay, and we did a worksheet based on that. And I said right at the end, close to the end of yesterday, don't let that confusion about how you have to be careful about calculating time intervals between two events distract you from the really interesting takeaway message from Einstein, which is the original result, or at least the the time interval between two events that are measured from different inertial reference frames depend on the frame from which they're measured. So I may measure 3 minutes between two events, and you might measure 2 minutes between two events, and that's something that no one would have thought of before these ideas were introduced. Okay. So now on, and we finished our worksheet there. So back to our muon discussion. Let's hope this is the front one here, yeah. So muons are a kind of unstable particle, and they're created in the upper atmosphere. They have a mass, if I remember correctly, about 200 times the mass of an electron. Other than that, they're pretty close in their properties to electrons, but they're unstable, and they decay quickly into an electron and a neutrino and an antineutrino, different kinds of neutrinos. Basically, the only thing you see after that is the electron. But we can detect muons, and so we can check as we go down the atmosphere. People don't really do this. They check it just at the surface of Earth. But if a muon is created here in the upper atmosphere and it goes down, it's going to decay at some point. Some of them decay really early, some of them decay later. If I have 1 million muons, half of them are going to decay after a time of 1.6 microseconds, and that's called the half-life. The half-life means how long do you have to wait for one of these particles to, or a million of these particles to turn into 500,000 of them. If you have a whole bunch of them, then how long do you have to wait for them to be reduced to half? And then if I wait that time again, they'll be reduced by half again, and so their numbers will go down really quickly. One thing I didn't point out yesterday is that because of this property, these muons behave like a clock. In other words, if somehow I create a million of these at the upper atmosphere, so up here, we create a million of them, we imagine, somehow in an experiment, and they're going down towards the surface of Earth, after a certain distance, half of them will be left. After another certain distance, half of them will be left again. And so I can determine, it's sort of like the ticking of a clock. Every time half of them are left, I can think of that as one tick of the clock. They're behaving just like the ticking of a clock. And as we've said before, as behaves the light clock, so behave all other clocks. And this is another, sort of weird clock of watching how many of these are left, but those are like ticks of a clock. And so there's a clock that we can measure. And this half-life that I'm referring to here, 1.5 times 10 to the minus 6 seconds, is if those muons are sitting at rest in the lab in front of me, they're not moving with respect to me, then that's how long it will take for half of them to disappear and turn into electrons. So we'll have only half the muons left. That's not necessarily true if the muons are moving at a high speed, because again, they're a clock, and that clock is going to tick more slowly as the muons progress downward through the atmosphere. So as I'm watching them from here on Earth, these muons, this ticking clock, are moving at a high speed with respect to me, 0.98 c towards the surface of Earth. And that clock is going to tick more slowly as observed by me sitting on the surface of Earth from the point of view of which that's moving. Okay? So the question we posed was, if we assume some numbers here, you're given the half-life, you're given the distance from the upper atmosphere to Earth's surface. Again, we're kind of idealizing. There's no one precise position of the upper atmosphere, but to keep things simple, we're going to imagine that a million of them are created 10 kilometers above the Earth's surface all at once. They decay with this half-life in the lab, and this is sort of a typical speed. We're going to assume, just for simplicity, that all of them are moving at 0.98 c directly downward towards the surface of Earth. Okay, so they're traversing that 10-kilometer distance. And the question we want to answer is how many muons would reach Earth in this case? They're decaying away. And so the question we have to answer is how many half-lives elapse as they're going down towards Earth? And then we'll multiply it by 1/2 that many times to see how many are left, right? We start with a million. We have it. If there's 10 half-lives, we multiply by 1/2 to the 10th power, or separately multiply by 1/2 10 times, okay? So you see this very table at the bottom of your worksheet that you're going to be filling in, and we've already done the work for the first part of this. This is pretend you're Newton. What would your intuition tell you about the distance they have to travel? Of course, the distance is 10 kilometers in this case. So from the point of view of an observer on Earth, and again, here in part A, we're assuming no relativistic time dilation effect exists. So we're just going to take the Newtonian point of view. How long does it take each muon to reach the Earth? So that 10 kilometers we can just fill in right away. And then to calculate how long it takes each muon to reach Earth, we just use distance equals speed times time. We can always do that as long as each of the distance and the speed and the time are from one inertial reference frame's point of view. We don't want to mix different inertial reference frames because the times might be different. We'll find out in the next chapter that you read about for today that the distances might be assessed to be different too. So we don't want to mix IRFs. But within one IRF, distance equals speed times time is always true. So if they're going 10 kilometers, that's 10,000 meters, and that's the distance they have to go. That's equal to the speed, which is 0.98 times c, 3 times 10 to the 8th meters per second, times the time it takes. So I can calculate the time it takes, and we did that last time. 3.4 times 10 to the minus 5 seconds. Now, the half-life is 1.5 times 10 to the minus 6 seconds. It's smaller than that. So several half-lives elapse on the way to Earth. And the question is, well, exactly how many? That's what's asked in part B. From the point of view of an observer, well, this is just asking for the half-life. Now, in this case, because we're Newton, we're going to assume, hey, the clock ticks at a certain rate, one tick every 1.5 times 10 to the minus 6 seconds if the clock's sitting in front of me. This is this muon decaying clock, a really weird clock. Newton's going to say, well, even if that clock is screaming towards Earth at 0.98 C, it ticks at the same rate. So the half-life is going to be exactly the same, according to Newton. That's not going to be true in the non-Newtonian case, but we're pretending just for comparisons purposes. Okay, and then one of the questions we answered at the end of last time was, well, given what the half-life is as observed by someone on Earth, and given how long someone on Earth sees them heading towards Earth from the upper atmosphere to the surface of Earth, we can figure out the number of half-lives. I just wrote the number symbol here. The time they have is equal to the number of half-lives times the time of each half-life, right? How many of these half-lives add up to the time that they're in the air before they hit Earth? And if you solve for that number, you get 22.7, right? Happens to not be a round number, but it's close to 23. And so here I filled in that data in the table so far. And the question we wanted to answer, and I just finished up with yesterday, was what's the number surviving at Earth's surface? Well, we started with 1 million. 22.7 half-lives elapsed, and for each half-life, right, if only one half-life elapsed, we would multiply by 1/2. If two of them elapsed, we would multiply by 1/2 squared, and so on. If 22.7 half-lives elapse, we multiply by 1/2 to the 22.7. It looks a little bit confusing, but that's easy to do in your calculator with that raising to the power function in your calculator. Put it in there. You can check it. Just make sure you're using your calculator the right way. You get 0.147 muons. Well, what is 0.147? Less than 1 out of 1 million. It's close to 1/10, right? What that means is there's some randomness in decay of unstable particles. So this means if you performed this experiment 100 times, only about 14 or 15 of those experiments would show even 1 muon reaching the surface of the Earth. And the other, 85% of the time, you would see 0 muons reaching the surface of the Earth. So we're not going to see much. Given that we created 1 million up there, almost all of them have decayed on the way to Earth because so many half-lives have elapsed. Now, this is not the true answer. This is not what you experimentally measure because it's from a non-relativistic point of view. So what I want you to do now is take, again, we're going to do the same thing we did in the non-relativistic case. We're going to take from the point of view of someone at rest on the surface of the Earth. So we're imagining we're sitting here. We're in very close to an inertial reference frame. We are technically moving in a circle, but it's not at a very fast acceleration rate. So we're in an inertial reference frame. And what's the distance they have to travel? Of course, the distance they have to travel is still 10 kilometers, right? That's not any different. Newton would measure that distance the same way Einstein's going to measure that distance, just by pulling a meter stick up to the upper atmosphere, however you would do that. So what I want you to do is both, all of the rest of the parts, which are the process of filling in this table. And I will probably stop you before you get finished with doing the point of view. So the idea in the third column is answer all these questions from the point of view of someone who's riding along with that muon clock and watching them sort of at rest as they're decaying. So since they're at rest, we know their half-life in that frame is exactly 1.5 microseconds because it's as if they're sitting with them in the lab, right? They're riding along down with them. Some of the numbers will change, some of them won't. So try that out. I'm going to put the folks on Zoom into a breakout room. So if you're video muted and you were going to the breakout room, you probably want to unmute your video room. I'm going to put you all in the same breakout room, and I may come check on you in a few minutes. Oh, sorry about that. I didn't realize I had passed the map before you got in. You know, and you're welcome. Just to make it a little bit more social in here, if you're close to someone, you know, once you've done a couple of these, you might turn to one of your neighbors, even though you're 6 feet separated from them, and ask them, or if you're having trouble getting started, you're welcome to ask me, but you can also ask your neighbors. Normally, I have people work in tight groups on these kind of things, and it makes it a point where lots of discussion happens. And I just feel like everybody's so kind of isolated in this new configuration. Maybe that's not so bad, but I certainly think it works better when you can talk it over with other people who are working on the same problem. Anybody having trouble getting started or with any particular parts? You mean how many half-lives expire on the way to Earth, or what's the way it's phrased in here in the question? Yeah, so if I were at rest with respect to the muons would have a half-life of 1.5 times 10 to the minus 6 seconds. Now, they're not at rest with respect to me if I'm in the Earth's inertial reference frame. They're moving really quickly. And since that half-life is an amount of time, and it effectively can be used as a clock, that half-life's going to get longer because each half-life is like a tick of the clock. And so those ticks, from the point of view of someone on Earth where the muons are coming really fast, are going to take longer. Okay, and so the half-life gets correspondingly longer in the same way the tick length increases, because each of those half-lives is like a tick of a kind of strange clock that's made out of decaying muons. No one would actually probably use a clock like that, but we can think of it as a clock. just so you have some way to check your intuition, I'm going to just show you what you should be getting for the relativistic case. And notice maybe the surprise punchline is that a whole bunch of the muons make it to the surface of Earth by virtue of the time dilation effect. And you can check that that number is exactly, you know, of course, the real experiment's more complicated because we're not just making a million of them and watching them decay, but they're continuously being made. But if you take all the details into account, you find the number reaching Earth are about the same. So the number of half-lives is only 4.5 about, rather than 22.7. So we're only cutting down by 1/2 to the 4.5 power. That's not too bad if we start with a million. Okay, how's it going here in the class? Is everybody satisfied with that second column in there? The third column you might find a little bit confusing because it's going to give us a preview of something that is associated with the chapter you read for today, which is those muons have to see the distance from the upper atmosphere to the surface of Earth as being smaller. Because they're traveling, we would call that in the context of chapter 6, the length contraction. But in this context, we're just going to see we have to back it out because everybody's got to agree on the number of muons that arrive at the surface of the Earth if we're using correct analyses. And we can analyze it from the point of view of the Earth inertial reference frame or the muon ones. So they're first going to agree that that number 44,000 doesn't change here. And therefore, the same number of half-lives must have elapsed on the way to Earth because they started as a million at the top and they ended up with 44,000 at the bottom. If they didn't agree on the 44,000, what would go wrong? Suppose I said, oh, from the muon, someone moving along with the muons, only 50 of them make it to the surface of Earth. Yes, the invariance of coincidence. I could, you know, have something like, if more than 1,000 of them arrive all at once, a nuclear bomb goes off and everything gets destroyed. But if not, then everything's the same. We come back later and we see if the bomb's gone off or not. There's only one answer that can happen there. Or if more than one answer is possible, we're going to have some logical contradiction with two possible future events happening that are not the same. So we're working our way up and then concluding that that distance from distance equals speed times time has to be less in this case, which accords with the length contraction. All right, I'm going to pull back the breakout room, so that'll take about a minute. And let's share screen again. Okay, I think everyone's back in the main room now. So let's go through the answers to the second column stuff that's associated with parts E through I, it looks like on here. So E asks, what's gamma for the muon motion relative to Earth? We're standing here on Earth. They're coming towards us at 0.98 c, so we do this usual calculation of 1 over the square root of 1 minus 0.98. Remember, 0.98 is V over C squared, right? And that's 5.025. From the point of view of an observer on Earth, how long does it take each muon to reach Earth? And in this case, the assessment's going to be the same as what Newton gave, because Newton measures the same distance as Einstein to that upper atmosphere. There's no difference about that because there's no relative motion involved. And Newton and Einstein are given the same speed, 0.98 c, so 0.98 times 3 times 10 to the 8th meters per second. And so the time, when we use distance equals speed times time, all from the Earth point of view, that time's got to be the same as it was in the non-relativistic case. The difference is the half-life of a muon. Again, the muon's like a clock. Every time half of them have decayed, that's like a tick of the clock. Half of them decay again, that's another tick of the clock. And in this case, we know how fast that clock ticks when they're at rest in front of us in the lab, or if we're riding along with them. But in this case, they're moving quickly towards us. And so their tick is going to be increased. The time it takes a tick to happen is going to be increased by a factor of gamma. So instead of being 1.5 times 10 to the minus 6 seconds, it's going to be 5.025 times that number. And that number is 7.538 times 10 to the minus 6 seconds. Okay. So here's how long they have. Here's how long each half-life is. And so if I want to calculate the number of half-lives that pass, I just divide those two. In other words, the time they're in the air is how many of these half-lives. And we solve for the how many. And in this case, we get 4.51. Not nearly as many as the 22.7 we got in the non-relativistic analysis. And that tells us if we calculate the number that are surviving, we do it exactly the same way, except, you know, if 2 half-lives had elapsed, we'd be raising to 1/2 squared. If 3 had elapsed, we would do 1/2 cubed. Here, 4.51 elapsed, so we raise 1/2 to the 4.51 power and multiply that by 1 million, and that tells us how much that 1 million gets cut down. And here, since it's only a handful of half-lives, it's not cut down too much. 44,000 muons are left. And so that's a huge difference between this relativistic analysis and the non-relativistic analysis. And you could do this experiment. It's more complicated in reality, of course, because you're not just all of a sudden creating a million of them, but they're being created all the time. But people talk about the muon flux, the rate at which muons are reaching the Earth. And you can compare whether it agrees with the relativistic analysis, which, you know, in reality for a real experiment would be a little bit more complicated. But it absolutely does very well agree with the relativistic analysis, which tends to tell us that this is evidence in favor of the time dilation. If you don't take the time dilation into account, you get a really wrong answer by a factor of 100,000 difference, right? Multiplied by 1 over 100,000 or so. Okay, let's go down and just together, because I don't know that everyone's done this, let's imagine what the things are being asked from the point of view of someone riding along with the muons. So they're in an inertial reference frame where the muons are at rest, and they're screaming towards Earth at 0.98 c along with the muons. Well, in that case, of course, the muon half-life is going to be exactly the same as was given in the beginning of the problem. It's still 1.5 microseconds because they're at rest with respect to the person who's making the observations here. Okay. Fill in the number of muons that this observer would have to say make it to Earth without decaying at the bottom of the last column. I asked this in class, I think, when the breakout room was actually in, I wasn't talking in front of the breakout room, but the answer has to be the same. If the person on Earth sees 44,000 of those make it to Earth, then, you know, that's a coincidence of 44,000 different events happening at the same time. Someone who's watching from the point of view of the muons and goes down with them says 44,000 of them have got to be left when I slam into the Earth. Because if not, I could have something set up on Earth that said, well, if greater than 1,000 of them hit Earth, let's blow up a bomb and the whole experiment gets destroyed. And we could come back later and say, which one of those happened? Was the experiment destroyed or not? Was it less than 1,000 or more than 1,000? And one of the answers is clearly more and less. So they've got to agree in this case. They can't disagree, or we could make some logical contradictions. Otherwise, it would lead to 2 different correct conclusions that were contradictory. So they agree on that last position in the 3rd column. The same number arrive at Earth, And now we have to ask ourselves, well, how many half-lives does that correspond to? In other words, starting with 1,000,000, I have to raise 1/2 to what power to get 44,000? And now you may not be an expert at solving these kinds of equations. If you're a math type, you would know you would use a logarithm to do this. But even if you're not an expert at doing this kind of thing, look at the previous section and you'll find out we did this exact calculation, except the unknown was over here and we put 4.51 up there. So the solution to this equation is that number that goes up there is 4.51, because we already saw this equation. We knew from the other direction it was easy to get the solution. Okay, so 4.51. Are you there?
Yes. Can I ask a quick question then?
Sure.
So I'm going to go back for a second, because part of the thing with the fact that it's exactly the same, the 44,000, is because the events from either reference frame match up, right?
Yes, I mean, so we could have a detector on Earth that reads how many muons in a digital display were detected, and it would read 44,000. Now, we could have two different experimenters in principle, one that was sitting on Earth and watched that digital display suddenly go up to 44,000, and another one who rode along with the muons and somehow avoid dying right when they got to the Earth because they were going at 0.98 C towards Earth. Somehow they survive, and they can look at the detector too and see that it reads 44,000. And they could, maybe make their own measurements right before they slammed into Earth and say, oh, I can see right next to me, there's 44,000 of them left. They've got to agree. There would be some logical contradiction. That's the principle of invariance of coincidences.
That's what I was going to ask. Okay, so the principle of invariance of coincidence is the one that's working here. Okay, thank you.
Yes, you're welcome. Okay, so now the question is, well, how much time elapses in this case if we have this many left at the surface of Earth and we have the number of half-lives that have elapsed? And sorry, I'm going the wrong way here. Given that the half-life of a muon at rest is 1.5 times 10 to the minus 6 seconds, how much time must have elapsed in the muon frame? So the muon frame is concluding 4.51 half-lives have elapsed for us on the way from being created to hitting the Earth. And so all I have to do is say how much time elapsed on the way to the Earth is 4.51 times the half-life that I see when I'm riding along with the muons, which is 1.5 times 10 to the minus 6, because I'm at rest with respect to them. So I should use the rest half-life. So we multiply those two together, and we get a much lower time, 6.8 times 10 to the minus 6 seconds. So from the muons' point of view, they're not going for so much time, or they're going for a much smaller time on the way from the upper atmosphere down towards Earth compared to what the people on Earth are assessing. People on Earth are saying, oh, they were up there for a full 34 microseconds, whereas the muons would disagree, or the person riding along with the muons would say, no, we were only in the air for 6.8 microseconds. That's because they disagree on their sense of how much time there is elapsing between events. Now, the kicker is, and what's going to lead us into chapter 6, is that now from the muon point of view, I can also use distance equals speed times time. Look, the time is different. The speed is the same, right? However fast the muons are seen moving towards Earth in the Earth IRF, the muons are going to see Earth moving upward towards them at that exact same speed. Right? So the Earth, in the muon frame, the Earth is moving towards them at 0.98 C. And so I know the speed, I know the time that elapses, and therefore I can calculate the distance from distance equals speed times time. And in this case, you find out from the muon's point of view, if someone in that frame could measure in a very careful way the distance from the upper atmosphere to the surface of the Earth, they would find it's only 2 kilometers. In other words, it's cut down by a factor of gamma. Gamma was 5.025. And that's an indication of what we're seeing in chapter 6 now, which is the length contraction. There's a certain length or distance from upper atmosphere to Earth. And when you're moving with respect to that, you measure it as a smaller length. Yes, Emily. Why, the question is, why does the time given here smaller from the muon's perspective and not from the Earth's perspective? Anybody want to help jump in and answer that question? Yeah, it has to do with what we talked about right at the beginning. I was reminding you of a big conversation we had yesterday, and at first it seems like it should be symmetric, right? I see your clock running slowly as you're coming towards me. You see my clock running slowly as I'm going towards you. But there's something that breaks the symmetry in this particular kind of example. What's the difference between, so we're talking about two events to give you a hint. There's an event, muons are created in the upper atmosphere. That's an event. And then there's another event down lower, muons are detected at Earth's surface. That's another event. And why can we not both conclude the same thing? Only one of those directions of conclusion is correct about who should assess having less time versus more time. Jack?
The Earth observers view the muons as moving slowly, but they still experience the same amount of time between events. That's as much of an explanation as I can.
Okay, yeah, so the explanation given was that the Earthlings observe the muon clocks as running more slowly. The key connection with what we talked about before is, when can I use just the time dilation without having to think about that asynchronization of the clocks? And let me back up in time here and go to the relevant conclusion slide, which is quite a bit back here on all my very busy slides, but it was complicated. Okay, here's the conclusion. We can use the time dilation formula. I'm looking right here at this sort of paragraph of stuff with the two bullets here. We can use the time dilation to compare the time interval between two events. You have to be clear about what those events are. Our events are muons created upper atmosphere, muons arrive at Earth. Those are two publicly identifiable events in this case. We can compare them, but only in the limited case where in one of the inertial reference frames, the events occur at the same location. So is it the Earth IRF or the muon IRF where the two events I just mentioned occur at the same location? The events are muons created in the upper atmosphere and muons arrive on Earth. One frame is sitting on Earth watching the muons move. The other one is riding along with the muons on the way down to the Earth. Who is seeing those two events happen at the same location? This is absolutely crucial, so it's great that you asked that question. Spencer? The muons, right. The muons are seeing them happen at the same location because it's the muons that are there. They're actually there as a word in both of the descriptions of the events, right? The muons are created, the muons were there. Muons arrive at Earth, yeah, the muons were there. So the muons are seeing them occur at the same location. Okay, so that's true. This first bullet point is satisfied. And then how do we have to use the time dilation formula? We want to use the time dilation formula is used in the sense where that frame is the moving frame. In other words, that thing, normally when I'm thinking of using the time dilation, I think of, oh, there's a clock and I'm watching it move and it's ticking slowly. So here I'm going to say, if I'm using the muon frame, which is present at both of these events, I'm going to take it from the point of view where the muons are moving. And I will say, from that point of view, the muons clocks are ticking slowly and they're going to see less half-lives elapse on the way to Earth, right? They're going the same, they're going a certain distance, but they're going to see less half-lives elapse on the way to Earth because each half-life is like a tick of a clock, and that clock's going to tick more slowly. We can't conclude it the opposite point of view, where we take the point of view of the muons and we say, it absolutely is true. If you ride along with the muons and you watch the clocks on Earth, you're going to see the clocks on Earth and the clocks in the upper atmosphere, which would be synchronized from the point of view of someone standing on Earth. Those clocks will tick slowly as well. It's completely symmetric that way. The problem is the two events that we're talking about have clocks in two different locations, and they're going to be not synchronous with each other from the point of view of the muons. So at the very least, your takeaway should be, well, from that point of view, it's tricky, and I better not use it in that direction so naively. But in the other direction, there's only one clock, and so any asynchronization of clocks in different locations in the point of view of someone moving along with the muons, well, who cares? We're not using any other clocks that are moving down below the muons or up above the muons. We only have to use the clock that's right where the muons are at. Is that enough on that, Emily? Or did that just confuse it? Yeah, I mean, you have to understand the sense of what this second bullet means here. When I say the time dilation formula is used in the sense where that frame is moving, so you're agreeing that the frame that for which, and I'm going to turn off these sharing the slides so I can look at.
You're muted for us. Jim, you're muted for us. Jim, can you? Jim, you're muted for us.
I'm not sure how that happened, but somehow the mute button got clicked. As always, if something like that happens, immediately shout out, because somehow I clicked the mute button.
We were shouting out, but you couldn't hear us.
Oh, that's weird. So it was muted both ways somehow. In any case, what I was going to say is, the question is, why doesn't it go the other direction? In other words, the muons are seeing Earth's clocks running slowly or ticking slowly. And so from the muon point of view, naively, it seems like from the Earth point of view, they should assess less half-lives as having elapsed compared to the muon frame, but in fact, it's the opposite. And I'm not sure if you could hear me. You probably couldn't hear, so let me share my screen again to go back to this. I'm pointing something we worked really hard to get to on this slide back from yesterday, and that's that you can't just willy-nilly use the time dilation formula to conclude something about how to compare time intervals between two events as seen by two different frames, except in one very specific circumstance that tends to happen a lot in questions. So it's a very important circumstance, and that's the case that was illustrated up here. One event, you have something traveling between two locations that are in the same inertial reference frame. A second inertial reference frame is traveling between them, and the first event is when it leaves here, and the second one is when it arrives over here. So for us, that's the muons that are doing the traveling. They are present when they're created, and they're present when they arrive at Earth. So the muon frame only needs one clock. There's one clock moving along with the muons that goes across there. So the conclusion was, if there's one IRF in which the events occur at the same location, that's the muon IRF in our example here, we can use the time dilation formula as long as we use it in the sense where that frame, the muon frame for us, is the moving frame, and the Earth frame is the stationary frame. And what do I mean by that? Going to the board, that means when I write down the formula t prime equals gamma times t, or you could write it as the 1 over the square root of 1 minus v squared over c squared. But this is the simple formula. When I think of the muons as being moving, I'm going to say their tick takes longer. This is associated with how long I have to wait for a tick on the muon clock to go once. And that means the half-life for the muon is going to be longer, as seen from the point of view of someone on Earth where the muon frame is moving. their clock is ticking more slowly, and so a half-life is going to take longer. A half-life is a tick of their clock in this case, when compared to the half-life in the frame, you know, a tick of a similar clock just sitting with respect to me in a lab on Earth. And so this number is going to be smaller in this case. It's tricky. I mean, I can say the words 5 times, you know, just like some of those philosophy kinds of things. You can go through the 4 premises and the 3 conclusions and read it 8 times, and each time you get stuck at a different point in here. This is tricky. It's easy to confuse yourself on this. So the more times you can disentangle it for yourself, and I should say that this slide is not something that is covered in chapter 5 in Merman. This is something I added in because the last time I taught the course, a lot of people, you know, made objections at this point. And I thought, you know, we've already said that we shouldn't trust that events that are simultaneous in one frame are going to be simultaneous in another frame. So we already raised that specter before. So why not use it here to explain our way out of this, and then find that, you know, we really can use the time dilation in the naive sense as long as we're careful about exactly where we apply it. Okay, but you have to know what it means by using it in the sense of the moving frame. We don't want to imagine it from the point of view of the thing that we might just randomly see as moving, because from both frames, things are moving, right? In one frame, the muons are moving, and in one frame, the Earth is moving. But in this case, what I'm saying is the thing that's doing the moving between the 2 events, I want to look at it from the point of view where that is moving. And I want to apply the time dilation formula from that point of view, and I'll get the correct answer. If I apply it in the opposite direction, I'm not taking something into account with the asynchronization. Okay, great discussion. Lots to digest there. So this is our first really big chapter, and chapter 6 is no different. I think we finished up everything in this discussion. So let me flash forward in time. Sorry about that. And just sum up here with ways we might, you know, if somebody stops you on the street and says, well, what's the time dilation effect? Quick, tell me. You might very quickly say, well, it says that moving clocks run slowly. Well, that's okay. I mean, there's some truth to that. Like any statement, you have to disentangle exactly what you mean by the words. You can't see it here, but I actually put an X, should have made it more bold. I put an X through this. It's not such a great thing to say because it seems to suggest that a moving clock is actively behaving differently than a clock at rest. And there's nothing active about it. You know, a moving clock feels just the same as a clock at rest because there's no difference fundamentally between rest and movement. Movement is just someone's biased point of view from the point of view of the thing moving. Yeah, so a clock is behaving exactly the same. So we don't want to, you know, there's nothing inherently wrong with this. I don't know why that happens, but somehow I have to reset this pointer. Nothing inherently wrong with saying that as long as you understand what it means. So we might be a little bit more careful and be tempted to say, well, moving clocks just appear to run slowly. But there's kind of a problem with that statement too, because it seems to suggest that the slower motion is only apparent and the real rate is the rate at which is observed to run when it's at rest. But that's not true. I mean, things aren't apparent when they're moving with respect to us and real when they're sitting at rest with respect to us. They're just 2 different measurements where they're behaving as they naturally do in both cases. So it's hard to see on here, at least in the classroom, but I've drawn an X through there. I'm not saying it's wrong. I'm just saying, well, you need to explain a little bit because it sounds a little bit misleading there. So, well, here's a big statement, but I'm trying to be very careful and precise about what I'm saying here. To rephrase the same idea, a clock ticks at a slower rate when observed from an inertial reference frame in which it moves, compared to the rate when observed from an inertial reference frame in which it's at rest, or which it moves more slowly. It could be the same exact clock, and it's not doing anything differently. We're just saying how it appears when someone stands at rest with respect to it versus how it appears when it moves. And when I say appears, I'm not saying it's not real. I'm saying that's exactly how it is. It's the behavior of the clock in both cases, and neither case is more real than the other. Okay, I thought I'd just finish up with some reading responses, and then we'll get into a tiny bit into chapter 6 today. We'll continue on with that tomorrow. Because we've set up a lot of the things that we need to consider in chapter 6, there's still a chance we might finish chapter 6 tomorrow. In any case, it's not on the exam. There's no rush to do it. The exam covers only through chapter 5. So here are 3 reading response questions. Does one clock really run slower than the other, or is it just observed from a particular perspective to tick more slowly? What do you say about that one? I put it here because we really just said something to that degree, right? Does it really run slower? Well, I don't know. It can't both. If we're saying really, that makes it sound like there's one fundamental reality in which it really runs more slowly. And in this case, you know, it doesn't really run more slowly, or it's not doing 2 things at once. Rather, it is being observed from a particular perspective to tick more slowly, and from another perspective to tick more quickly. That would be the point where it's at rest or moving at a slower speed. Second one, it almost seems as though these clocks know how fast they're going and can speed up and slow down accordingly. What do you say about that? Yeah, Jack just said, well, I don't know how fast I'm going, and the clock is no better off, right? I feel like I'm at rest now. Everybody, when they're in an inertial reference frame, feels like they're at rest. So there's nothing you can do to behave differently when you're moving, because when you're moving, at least with uniform velocity, you feel exactly the same as when you're at rest. And Einstein is saying it's not just that you feel that way, there's fundamentally no difference between moving uniformly and being at rest. So the clocks don't actively do anything. They're just behaving the same way. We're observing them from different points of view, and that's something that the fact that we get different observations, it disagrees with the notion of universal or absolute time. Finally, I'm interested in the inserted comment on page 41. Merman says, several people asked this question, by the way. Merman says it's not relevant to wonder what happens if we bring the 2 clocks together again after the experiment to see how big the gap is. Yeah, that's something I think Jack mentioned earlier on, or maybe it was Everett. The idea is, well, one's running slowly, one's running quickly. Let's bring them back together, or at least bring someone together who is in the slow moving point of view and ask them what they see on the other person's clock. And so this corresponds to something, doing this exact thought experiment. No one's ever performed it with a human being because we just can't travel that fast, technologically speaking. But there's no contradiction there. And if we imagine the Earth sitting here and someone going on a spaceship far away, and that spaceship comes back around, we're going to find out that actually the person who is doing the traveling away from Earth ages less than the person on Earth. The person on Earth is older. So it's called the twin paradox because we imagine identical twins do it, and then one ends up 20 years older than the other when they come back together, which is amazing. Why isn't it symmetric? It isn't symmetric because one was in an inertial reference frame the whole time, whereas the other one went out and then switched inertial reference frames and came back, so that we break the symmetry. It's not exactly clear right now how that's going to help us, but breaking the symmetry that way means that they don't have to behave the same way in terms of their aging. We'll get to that. Merman doesn't discuss it till like chapter 12 or 14. We'll get to it at the end of chapter 7. We'll be in a position where we can discuss the twin paradox then, so next week. All right, and that's the end of chapter 5. So I'm going to stop that, close this out, and then we'll just do a little bit in the time we have left of chapter 6. And while I'm bringing it up, any questions? I should say, you know, I haven't looked at your reading responses for chapter 6 because I knew we still had a substantial amount of chapter 5 stuff left. But the chapter 5 ones, keep digging deeply into those ideas. I don't want you to summarize what Merman is saying, but rather, if you have a question, that's a great way to do a reading response question. If you really think Merman's wrong or you've got him caught in some logical contradiction, try to flesh that out and write a paragraph about exactly what it is. What's the cognitive dissonance you have? How can these 2 things simultaneously be true? and not cause a logical contradiction. That's the kind of stuff that's really important, because then you'll be set up, if we can untangle that in class, you'll really remember it if you've really caused yourself to see it looks like a contradiction ahead of time. Okay, let's see. Slideshow from current slide. Oops, that's not what I wanted to do. I want to share screen first for the Zoom folks, and then let's do slideshow mode. And let's do it in a slightly different way. Oops. Sorry, technical difficulties here. I want to make it so that in my video, it's not obscured by that bar in Zoom. I think this should work pretty well. Okay, so Chapter 6 is going to go back to the idea of a stick that's moving but instead of what we did in Chapter 4, where it was moving perpendicular to its length, here it's going to be moving parallel to its length. And the claim is, the initial goal is to prove what Merman calls Rule 3. I would call it length contraction because I can never remember what Rule 3 or Rule 6 means, but we'll just call it the length contraction effect. If a meter stick has length L when it's stationary, like that doesn't mean it's stationary. When I say something stationary, I mean when viewed from the point of view where it's at rest in that IRF. Then when it's observed from a different IRF in which it's moving at a speed parallel to its length, it has a contracted length. And so we want to figure out where that formula comes from. We saw that effect in the distance from upper atmosphere to Earth being contracted from the point of view of the muons. And that's a general effect. So here's the approach that I think Merman outlines. First, we got to find out how fast a light clock ticks when it moves parallel to its length. We already did this calculation for when it's moving perpendicular to its length, and we found out it slowed down, right? Very early on, qualitatively, we found that out. And then the last chapter, we found out exactly how much it slows down. So let's first do that and address it. And so here's what we're going to do. We're going to take one of these light clocks with the two mirrors, and one of them is going to be oriented in the direction perpendicular to which it's going to be moving. And we're also going to put next to it one that's oriented parallel to the direction that it's about to start moving. And we're going to have them move together. So now I start viewing them from the point of view where they're moving to the right. So let's imagine I review that same clock as it's going to the right, maybe 99.5% the speed of light. And the two clocks we already know that this one on the left here should be ticking slowly right here. And the question is, does this one tick any more slowly, or maybe more quickly, or maybe it doesn't change at all? The argument here is that it has to tick at the same rate. And what's the reason for that? This is just one of those look at it and think about it for a second. Jack? Yeah, Rule 1 tells us that when a meter stick is moving in the direction perpendicular to its length won't change. This one we're about to show, its length does change. So when we look at it, this isn't a correct point of view. We should really show that other one as being shorter, but we haven't proved the effect yet. And yet somehow Merman is concluding right away that these have to tick at exactly the same rate. So in other words, whenever this one comes up and comes back down and hits the bottom, this one's going to hit its bottom part at exactly the same time. They're going to tick in lockstep. Even though one of them's moving and has gotten shortened, we're going to prove that in just a second. What's the principle, hint, that tells us they have to correlate like that?
It's probably one of my favorite principles.
Yes. So Jesse just said what I think Spencer said before, which is, I don't remember the name of it, but it's the one where if events occur at the same place in the same time in one frame, they have to occur in that way in the other frame. And that's what Merman calls the principle of invariance of coincidences. Okay, and if you can't pull that name out of your head, that's fine. When I say that name, you should know what I'm talking about. But if you can't pull that name out of your head, that's not something I really care about. I'm not sure I haven't looked to see if that's something that only Merman uses that terminology or if it's in common usage. I just don't remember seeing it in other books on relativity. Okay, so these two are going to tick in, oops, that's not what I wanted to push. These two are going to tick in lockstep. In other words, if we start them leaving at the same time, they're both going to come back and hit their lowest point at the same time. And that's the principle of invariance of coincidences, which is Professor Katavid's favorite principle, apparently. So that was easy. We're halfway done. Well, not really. That was the easy part of it. We're halfway done with the numbers. Now we got to prove that we're going to use this light clock to deduce the length of the moving light clock. In other words, we already know that this clock is going to slow down because the one oriented vertically, we already proved that that one slows down. So this one's going to slow down too if they're ticking in lockstep. And somehow that's going to tell us that this has to be a shorter distance. And you've already done part of the setup in your homework. That was the point of, an otherwise kind of obscure homework problem where they had a meter stick moving along its length. You've done some of the algebra associated with this, and we're going to do the rest of it right now. Okay, so let's imagine here's this light clock that's about to be moving to the right, and let's suppose it's at rest with respect to us, and in this frame where it's at rest with respect to us, its length is L. So we would say its rest length is L. It's ticking back and forth like that. We'll call the frame where it's sitting at rest frame F. And I'm going to call frame F prime the frame in which it's moving at a different speed along the direction of its length. Okay? And we already know the tick length, T prime, is going to be different in this frame in which it's moving. So I'm going to draw that generally as green here. So if I click forward to the frame F prime position, well, here it's moving. And instead of an animation, I just copied the picture out of Merman's book, which is showing that here is an early time. Now, I'm not sure anything about the length of this meter stick, so I'm not going to assume it's length L anymore. We're going to call its length L prime, when our goal is to figure out what L prime is compared to L. But it's moving along. So here it is at one instant in time where the light pulse happens to be just leaving the back end of it and heading towards the front. But while it's heading towards the front, of course, the front of the meter stick moves along too. And so before it gets to bounce, it's like, I will say, it left the back of the bus, but the front of the bus was moving while it was heading towards the front of the bus. And so it doesn't really hit until some later time. It doesn't hit the front of the bus right here. It has to, the front of the bus has moved up here by the time it hits the front of the bus and reflects going to the back. Merman says, let's call that time between these two snapshots that we've taken here, time t0. And then as it goes back to the back of the bus, that doesn't take nearly as much time. There's a much shorter time because in this case, it's not running towards the front of the bus as the front of the bus is running away. It's running towards the back of the bus, and the back of the bus is running toward it. So there's a much shorter time, which Merman calls T1, between these second and third pictures that we have there. And our goal is to figure out something about T0 and T1. And since you have done this, was this in the chapter 3 homework? Yeah, it's not in the chapter 5, it's in the chapter 3 homework. So everybody's seen this now. And so I'm going to be, not so careful about it because I'm hoping it looks somewhat familiar. We're trying to calculate something about these two times. And our goal is, well, look, if we add those two times together, that's the time for an entire tick of a moving light clock. And we already know that the time tick of a moving light clock, which is the sum of those two times, should be equal to gamma times t, where t is the tick length of the light clock when it's at rest. So we're going to use that later on. Okay, focusing on this distance that the pulse has to move. You did this in the homework. And just using distance equals speed times time, the pulse is moving at the speed of light. That tells me some relationship or some way to calculate t0 in terms of d0 in terms of t0 and c. Then I could separately say, let me calculate the same distance a different way. How far the light pulse has to move? Well, it's got to move a distance L prime, but it's also got to move an additional distance, which is the distance the front of the meter stick moved in time t0. And so the distance it has to move is, there we go, is L prime plus the distance that the front of the meter stick moved in the time between these two frames, okay? And so those two things are equal because they're equal to t0, so I set them equal and I can solve for t0. And when you do that, you get t0 is L prime over c minus v. For the people I talked to who are doing this, that looks familiar, I hope. Then there's a similar calculation. You're doing exactly the same thing in between the second and third picture frames that show there, right? Here's the distance it has to move. It's moving at the speed of light, and therefore the distance it moves, which is I'm calling d1 here, is c1, sorry, I should back up, is c1 times t1, which is the amount of t1 is the time between these two frames. So one way to calculate that distance is c1 times t1. The other way of calculating it is saying, well, it doesn't have to quite move L prime. It only has to move L prime minus v times t1, which is how far the back of the bus moves. And so we write that down, and then we set the two equal, and we solve for t1, and I'm putting that result up here. And again, if you were successful in that homework problem, you saw those two relationships. And what do we do after that? Well, we're going to say the total time for a back and forth tick, that's the time length for a full tick of the light clock, is the sum of those two. So when I add those two together, t0 plus t1, I get this expression. And that should be equal to, since that was t prime, that should be equal to some longer tick length than the tick length of the light clock, which is represented by t, in the frame in which it's at rest. And then what do? We got a common denominator for the two. I'm skipping the details here because you did this on homework. But if you get a common denominator, we multiply the left one by c plus v over c plus v and c minus v over c minus v and do the algebra. The common denominator ends up being 1 minus v squared over c squared. The numerator, after some algebra, it's probably not worth going through that. But if you want to see it, I'm happy to show you. I've been through it with a couple people on homework. Then my goal is to solve for L prime, right? We're looking for what the length of this thing is in the moving frame. That's what we call L prime. So we're going to solve for L prime. And when I do that, notice in this particular case, I've got a square root of 1 minus v squared over c squared in the denominator. If I multiply this up in the numerator on both sides, it will cancel on this side, and I'll get a 1 minus v squared over c squared in the numerator. And if I divide by the square root of that, I'm left with a square root of that in the numerator. And you'll see that happen in just a second, right? If I take 4 divided by the square root of 4, I'm left with a square root of 4, which is 2 in the numerator, right? Or if I take a 5 divided by the square root of 5, that just leaves me with a square root of 5 in the numerator. So that's what we're seeing here. And the only other thing I've done is divide by, so I already had a t over here. I'm going to divide by 2 and multiply by c, and that gives me this factor out in front. And we're almost done. The key observation now is that this factor up here now can be, what I wanted was something that relates L prime to L, the length of this meter stick in the frame where it's not moving. And that can be gotten by this relation up at the top, which is to say, I guess I just sort of spaced out in talking about it. If you look at this thing just sitting at rest, it has length L. And so if the pulse is moving at speed c, it has to go 2L in a back and forth tick, right? So 2L equals CT. And that means that CT over 2 down here is just L. That's another name for L. And so that's telling us that the length in the moving frame is equal to the length in the rest frame times this factor, which we now know to be 1 over gamma. Gamma is the one with the 1 over square root, so this is a 1 over gamma. Gamma is bigger than 1. It was 5 in that previous example. So this is it. If gamma is a big number, this is a small number, right? This is a number that's always less than 1. So that says the length in the frame where it's seen as moving is less than the length in the frame where it's at rest or in its rest frame. And so this is Merman's rule 3. If a meter stick has length L when it's stationary, then when observed from an IRF in which it's moving at speed v parallel to its length, it has the contracted length L prime equals L times 1 over gamma. And since it's just past 11 o'clock, let's stop there and we'll do the first worksheet tomorrow. I've actually got 2 worksheets, and they kind of parallel the first 2 worksheets that we did on this, and that will probably take most of tomorrow. I'm hoping you guys find this really exciting, because this is another counterintuitive thing that you never would have guessed, that things shrink. And the questions that should come to mind are, do they really shrink, or is it just an apparent shrinking that happens? Do they really slow down, or is it just apparent? And that's the kind of thing I was addressing at the end of the last chapter. You can get a lot of mileage out of that. All right. If you're not hanging out for office hours, then I'll see you in the Zoom meeting for Dr. Kadavid's class today. Normally we wouldn't have one, but we're doing a makeup Zoom meeting today, so see you then.